International Center for Theoretical Physics for the breakthrough contribution in the area of optical sensor and waveguide. He also received DART Fellowship awarded by Germany, JSPS Fellowship, Japan, and published more than 100 research papers in reputed international journals. 9 PhD scholars and 1 postdoctoral fellows are working under his supervision. So let's welcome to our speaker, Dr. Rajan Jha. So hello, sir.
Thank you. Can you hear me?
Yes, I.
Yeah. So can you see my slide?
Yes, it is.
Yeah. So thank you, Upen, Dr. Upen, for the introduction. So first of all, good morning, everyone. It's nice to be, in the virtual mode, giving the presentation. The pain of traveling is to some extent reduced, but at the same time, the merit or advantage of interacting with the faculty members and visiting the lab is more painful. So I must take this opportunity to thank head of the department, Professor Akhilesh, in particular, for this opportunity to present some of our research work, keeping in mind the theme of the conference, or this online workshop, I should say, of this faculty development program. So the topic of today's presentation is photonic crystal fiber based interferometric system, lab to land. So the whole idea, what I will be sharing with you today, is can we have photonic crystal based systems which can be utilized for some of the practical applications. So I'm coming from not really old IIT, like 11, 12 year old, and the research lab in which we work is named as Nanophotonics and Plasmonics Laboratory. So what we do in our research lab, these are some of the broad areas of research which we are into. One is plasmonics. So we do all type of plasmonics application in our lab, which are basically if you take a metal dielectric interface and try to incident some proper polarization of light at such interface, you tend to excite some electron at these interface. Those are called as plasmon. That is, the collective oscillations of electron at the interface are called plasmon. And if rather than having this film of metal and dielectric, if you have a nanoparticle of metal, then you tend to form what are called as a hotspot, as you can see around these zones, reddish and slightly yellowish in color. These are hotspot. That means you have a lot of evanescent field, a lot of, I should say not evanescent field, I should say a lot of electric field that are present around. So if you get anything closer, or if you get any medium which is closer to this hotspot, so this will going to disturb the electron cloud. And therefore, those disturbance in the electron cloud can be measured as a resonance case, leading to thereby such all the different type of study what people have been observing, whether it is for biological application or for biosensing application, or in general applications of metallic nanoparticle. So this is one area what we also work in our lab. Another area in which we are working in our lab is interferometry. So what we do in our lab, we do some sort of controlled excitations of specialty fiber or a special type of fiber modes to create interference pattern. And then in this view graph, as you can see, this is what one type of knot resonator, which is basically called as a square knot resonator or reef resonator, which we developed, which has been developed in our lab. And as you can see that you have 4 arms which are associated. So these can also act as an add-drop filter, and these can also be used for monitoring different parameter or detection of different parameter for sensing application. Of late, in last couple of years, we have plunged into a area of what is called quantum photonics. Here we are basically trying to develop a system where can we have a single photon, controlled single photon emission at room temperature, and how to collect those single photon emission. So what I have tried to show here is the limitations of what the existing single photon source and the corresponding detector has. That means the coupling efficiency is very poor. You can see out of the, let's say in this schematic diagram, which is not really up to the scale, You have a semiconducting nanowire, which is on the interface of connected to attached to some of the reflecting surface, and then you have a photon detector. So basically, the photons that are emitted by the quantum dots, you will see that only part of them are going inside, rest are going away from that. Thereby giving you, although you can able to create single photon using these quantum dots, but then the problem lies is you don't have a poor coupling efficiency. So we are just trying to see that how to address this part. In today's talk, I will be mostly confining to interferometry. I hope my slides are moving for you, because in some other talk the other day I heard that slides not moving.
Yeah, it's
slide.
moving.
Okay, good. Thank you. So in today's talk, we'll be discussing our, as per also the title that I shared, it is on the interferometry. So let me just give you some brief outline what I will be talking about in today's talk. I will start with introduction, and these are some of the applications which I will show you and its potential, taking from lab to land. So these are some of the area in which I will be discussing, like nano displacement, sensor and accelerometer, strain gauge, gases detection, fluid flow measurement, and then followed by conclusion. So to start with introduction, just let me, since we are talking about photonic crystal fiber, or also called as a specialty fiber, or also called as a microstructured fiber, let me give you a brief introduction about what are photonic crystal. So if you see, this photonic crystal are basically some sort of arrangement of, I should say, some dielectric. So if you have dielectric which are arranged in periodic fashion, as you can see here, green, blue. So these are periodic dielectric. The refractive index and the thickness of these can be, of course, optimized for different depending upon what you want. So photonic crystal are basically periodic arrangement of dielectric. So if this periodicity periodicity in one dimension, that means it is in 1D, then it is called as a 1D photonic crystal. However, if you have the periodicity in 2D, the classical example is the chessboard that we used to play. Then those, you can think of those chessboard as a 2-dimensional photonic crystal. And if the periodicity continues in 3 dimensions, that means the dielectric, 3 different dielectric are there, and it is periodic in 3 dimensions, then those are called as a photonic crystal in 3 dimensions, periodicity in 3 dimensions, or 3D photonic crystal. The point is, all these periodic system that you consider, we know that from the standard Maxwell's equation, we can derive the wave equation. When we derive the wave equation from a standard Maxwell's equation, then we can first derive it in, let's say, whenever we start, we first derive it in vacuum, and then we try to introduce the material aspect or the medium aspect into the wave equation, where mu and epsilon start coming into play. So if you consider a non-magnetic media, then you tend to have, mu equal to 1, and then epsilon become a function in the wave equation. Epsilon appears in the wave equation, and that epsilon is what is the dielectric constant or dielectric which is defined. So let's say this is epsilon 1, this is epsilon 2. So starting from the Maxwell's equation, one can write a wave equation which will satisfy certain solution, so that the light will able to propagate inside such type of periodic arrangement. So these are some of the solutions, or I should say harmonic modes, which basically are supported by such type of photonic crystal. So if we consider photonic crystal fiber are basically photonic crystal in 2 dimensions. That means 2D photonic crystals are called as photonic crystal fiber. That means the periodic arrangement is in 2 dimensions. Now, when I say periodic arrangement is in 2 dimensions, you can visualize this photonic crystal fiber as a candle. Let's assume it as a candle. We know the candle that what we use to light when there is no power. You can think it as a candle. Now this candle, if you pierce a needle from one end of the candle and get the needle from the other end out, you'll see that if this piercing of the needle in the candle is periodic in certain, because we have to create photonic crystal, so there has to be some periodic. So if you can pierce this if you can pierce this needle from one end, base of the candle, and get the needle out from the other base, then what if it is repeated in periodic fashion, or if it is periodic, the structure is periodic, then what you expect, what you will see on the cross section is something very similar. What you can see here. That means you'll have somewhere you'll have air because needle has been pierced, somewhere you'll have wax. So the periodicity in wax and air, if it is in hexagonal pattern, I will discuss about that, why we use hexagonal pattern, then such type of periodic arrangement thought of in a needle, as thought of in a wax, can be visualized as a photonic crystal fiber. That means you have a periodicity of air as a dielectric and wax as a dielectric in certain pattern. So these are basically of two types, solid core PCF and one other is hollow core PCF. What are the different advantages we have about these with respect to, let's say, the fiber that I used for mostly for communication application? These are some of the advantages, because you have design flexibility. You know what is the diameter of the air hole that you want. I mean, if you use a thicker needle, the hole diameter will be more. If you have a thinner needle, the hole diameter will be small. Now you can modulate, you can tune the distance between the two holes, and those are called as d by lambda ratio. That means the diameter of the hole divided by the distance between the two holes are called d by lambda ratio. So you get to change the d by lambda ratio, and therefore the whole wave propagation behavior or the dispersion characteristics of the waveguide changes, or the such type of photonic crystal structure changes. Further, like the optical fiber that we use for wide applications, most of all these fibers have certain dopants in the core in order to enhance the refractive index. But in this particular case, there is no doping. I mean, core is free from doping because you have air and then you have a silica. The fiber is made up of silica, therefore you have air and silica as such, and there is no dopants. As you have more air there, therefore these are less temperature sensitive, because you have air plus silica, so only silica will contribute to the temperature variation. Therefore, such type of probe can be utilized for all low temperature device applications. And moreover, the mode area can be tailored by properly tailoring the d by lambda ratio. So these are some of the broad advantage of photonic crystal fiber, which is a two-dimensional photonic crystal. And these advantages allows it for wide range of applications. The only disadvantage is still the development or fabrication of PCF is costly affairs, and the PCF that we purchase is also costly. Okay, let me go slightly bit more into this PCF. So if I consider, so as I mentioned in the last slide, that you have two types of PCF. One is solid core PCF, another is hollow core PCF. So here what I have shown you is a solid core PCF. So solid core PCF works on the same principle. So you see that these are air holes, these are silica. These are air holes, so there is some periodic arrangement. Now, why it is hexagonal periodic arrangement there has been done, because this makes the fabrication process easier, and also the calculation that you do, which to understand that what type of modes will be supported by such type of periodic structure becomes much easier. So both fabrication wise, experiment wise, it is easier. If you want to do theoretical study, then also considering such type of structure is easy. Therefore, what does it work? It works on the same principle as that of the conventional fiber, that is total internal reflection, but then we say it as a modified total internal reflection. This is MTIR, which is modified total internal reflection. Now, the point here is why we say modified, because please note, in the center, which is solid silica will have higher index, right, as compared to air, silica, air, silica, air, silica. That means these layer just near to the center solid will have an index which is lower than the center, and therefore again it is total internal reflection getting fulfilled. But it is called as a modified because now you have slightly different way. You do not have a single cladding like what you have in the conventional fiber. You have some portion of silica, some portion of air, but the effective index of this ring, or the effective index of this one, will be lesser than this, thereby satisfying the total internal condition. So this is what is called as a solid core photonic crystal fiber. So this typically shows you that how does the mode profile look like, that how do you have the mode which is being guided inside the optical fiber. Now, if I go to the light confinement, why the light, how the lights are confined. So you please note that if you have the light in the center, you know from quantum mechanics that there is what is called as tunneling concepts. So you have light which will tunnel between these air holes. You have silica, so light will tunnel out through this. You can see that it is tunneling out from here, it is going to air, and then it passes further from, it can also tunnel out through these space in between, as you can see in this. So what I would like to tell you that the one that is tunneling out, if you can also remember, the tunneling out is always associated with the higher order modes because those are less confined. It's easier for them to, you know, get coupled to other system. So these lead to some sort of a tunneling, and also thereby it both lead to, you know, both this structure, either it is through the holes or through the silica region. This leads to the confinement loss. That means the fundamental mode, the power in the fundamental mode will be less, and there will be less confinement. Now one can control the confinement by increasing the hole size or by adding more, you know, ring. So one can tailor. This is where the beauty of photonic crystal fiber lies, that you can tailor the property depending upon your requirement. So this is what confinement about. Then comes to the another type. These are the two, I mean, what I have discussed, that solid core fiber, PCF, and hollow core. So these are the two broadly classified region, broadly classified type of fiber. Of course, there are other type of also polarization maintaining PCF and stuff, but these are broadly category. Now, how is hollow core fiber, also called as a photonic band gap fiber, are different than the conventional fiber or than the solid core photonic crystal fiber? As the name suggests, in the center you have the hollow region, but here the guidance is unlike MPIR in the solid core photonic crystal fiber. Here the guidance is band gap guidance, and one can visualize that how is it possible that in center, if you have air, light get guided through the air, although around the central region air you have the some again periodic structure arranged in hexagonal lattice. So the working principle is, if you have multiple rings around the air center, as you can see that there will be reflection from each interface. So more the rings, more stronger will be the more the rings, more stronger will be the reflection. Therefore, a particular band will only allow to propagate inside the fiber or hollow core photonic crystal fiber. That means out of the broad wavelength source, if you launch at one end of the fiber, you will realize that only a band which is fulfilling these conditions will able to pass through the optical fiber. So these are therefore called as a photonic band gap. It allows only a band to propagate, and it allows rest of the band will get blocked. So these are the way in which, you know, you have these different type of PCF. Let me give you some of, I mean, show you some of the fabricated structure that we have, that we have obtained in our lab. These are shows you some micro and nano fibers. These are some wrapped microfibers where you are wrapping one around the other. These are some knot resonators. These are some square reef knot resonators I have shown you. These are some metal coated. If you coat metal for PCF to excite those plasmon modes, it can be utilized for that. This is something which I will discuss in more detail, that how you can control, different, I should say, the modal excitation in order to obtain the interferometry. And then these are some of the, you know, these are, you can see that these lines are the basically air, solid silica region, or the air holes which you are seeing here. So what we have tried to trap some air bubble inside the fiber. So these are basically inline micro air bubble or cavity that has been created inside the photonic crystal fiber. So these we do have a lot of other structures that we develop in our lab depending upon our requirement. Okay, so let me come back to something more fundamental, which I'm sure that all of you must be aware about. But let me just, you know, brush up, and also to make the story complete, you know, let me introduce you to the concept of what is called as interferometry and how one can achieve this interferometry using this photonic crystal or two-dimensional photonic crystal called as a photonic crystal fiber. So what is interferometry? If I take a light and if I add light to a light, this is what Feynman has said. So if you add light to a light, you get some light or you get no light. So you may get some light or you may get no light. So when you will get some light or when you will get no light will depend upon whether the two beam or the two light are, how they are adding up. If they are adding up suitably, then it forms what are called as a constructive interference. And if they are adding up in a destructive fashion, that means the phase, it is out of phase, or the phase difference is some integral multiple n plus, sorry, the part difference is integral multiple of half lambda, then you have what is called as a destructive interference. Now, depending upon how you use this phase part of the interferometry, gives you all these different type of interesting phenomena. Now, the important point, what I would like to discuss here, this is the conventional interferometry. Now, but think of a situation that I want to have interferometry using single mode fiber and photonic crystal fiber. So what we'll do as follows. Now, this is the working principle of the whole different applications that I will show. So this is an important slide. So you see, if you have a single mode fiber, just consider any conventional single mode fiber. This is FMF28E, that's what we generally consider. And then you have a photonic crystal fiber. In this case, this is a solid core photonic crystal fiber. As you can see this line here, the center is a solid core. And then you have these you have air holes which are all along the length of the fiber. Now, suppose if you launch the fundamental mode at some wavelength, if you have a broad SLED source, let's say at 1310 or 1550, and if you incident the source here, then you know that the single mode fiber, as the name suggests, it will only support fundamental mode. And these modes start traveling along with the maximum intensity in the center. Now, as it comes at the end of the SMF and before PCF, what we have done that we have fusion spliced, we have heated both two at a very high temperature so that both will going to fuse. Now, as it fuse, SMF and PCF fuse, so you can think that as PCF will fuse, air and silica will melt together to give you some silica. Something like if you even melt the candle having air holes with wax and air holes, if you melt the candle, it will only give you wax, air holes will collapse. Something very similar here. So you have what this red region is what is called as a collapsed region or collapsed length. Now, this is very important to basically excite the modes in the different modes in the PCF. Now, so what happens that suppose you give 1.5 micron light sources here, it comes here, and now this is, if you can suitably fuse them, then the length of this can be controlled. In our lab, we can control from 5 micron to 500 micron. Of the length of this can be controlled in such a way that this 1.55 micron size is comparable to this solid region, or it is also called as a no core region, or it is also called as a collapsed region. Since this red portion length is comparable to the wavelength, we know that light will going to get diffract. Now, as the light diffract, the light is no longer confined to the core of the PCF. It's also get into the cladding part. Now, you know that the core of the PCF will have certain indices which is different than the cladding of the PCF. Now, if two medium have different indices, that means the wave that will propagate with a different velocity for a given length of the PCF. Now, for a given length, core mode, which is going through the core, and the cladding mode, which is passing through the cladding, will accumulate some phase difference because both are traveling at different velocity, but the length of the PCF is same. Therefore, still it will accumulate some phase difference. Now, depending upon what it excite, depending upon whether the excitation can be either the two core mode, it can have more than one core mode. So interference will be between the two core mode of the PCF. That depends upon the structure of the PCF. Or interference can be between the fundamental core mode and the higher order cladding mode. So excitation can be two core mode or core cladding mode. And therefore, if such type of excitation, we know that these modes will travel at different speed for a given length of the PCF. It will accumulate some phase difference, and it will going to give you, this is the view graph what I have shown here, is you see this is uncollapsed void, and this is collapsed void, which is solid silicon. This is the core of our SMF. So if you see the modes, these are the two fundamental core modes, or these are the core modes of any photocrystal fiber, the one that we have used in our system. And these are also core modes. These are two core modes. So either you get two core modes, these interfere to give you the interference, or you can also use the core and cladding modes. These are, you see, the core mode, and these are the higher order cladding modes of the PCF. So any of them can interfere depending upon the nature of the PCF to give you a very nice interference pattern, as you can see here. So you get something similar to what we have read in class 12, that if you choose things properly, if you choose the different parameter properly, you will get a very nice interference pattern. So this particular interference pattern, what I have shown here, is for a given length of a PCF. Let's say L is 1.2 centimeter. So as I mentioned to you that PCF is very expensive. Though it is expensive, but the length that are involved is very less. Therefore, it is not that difficult to use. So you get a very nice interference pattern. So what I have shown here is reflection in dB versus the wavelength. So you can please note from here that we are using a SLED source having some sort of 100 nanometer, I should say 100 nanometer width. And therefore, depending upon the condition of maxima and minima that is being fulfilled between the modes that are interfering, at some position, some wavelength lambda, you get maxima, and some other lambda, you get minima. Now, if you add, let's say, some other thing around this, that means if you have some, let's say, isopropanol, for example, is put around or is infiltrated, or some way you have done that. You have tried to interact or perturb the higher order modes with isopropanol, then you see that there is a shift in the interference pattern. One can monitor this shift in the interference pattern for characterizing the device for different applications. So this is the fundamental working principle of model interferometry based on two-dimensional photonic crystal called as a photonic crystal fiber. So please note that all these parameters like peak to dip, distance between them, FSR, all these can be very well controlled in our lab, depending upon what you want to do with that. Okay, so now I will proceed further, and I will show you that how this concept we have utilized for different applications. So first one is a nano displacement sensor. So if we say nano, this of course we have a nano vehicle which is now very well running on the roads. But if somebody has to imagine, a kid has to imagine how big is nano. So a nanometer is how far your fingernails grows in 1 second. So I'm sure that we are not able to see them, how fast your fingernail is growing, but this is something what you can visualize, that every second your fingernail is growing by a nanometer. Now, these nano displacement sensor has a lot of applications, and that was a motivation for us to develop such system, because also the ISRO is looking for such system. We have a project in our lab funded by ISRO. So I must acknowledge ISRO here. So why it is required nano displacement sensor? It is for the precision alignment and position monitoring. This is exactly what they are looking for. Of course, after we have done this work, I have read some papers where people have also tried to use. We of course propose this in our published paper that it can be utilized for non-uniformity on electronic chip at nanoscale. So it is an alternate. It is an alternate to the profilometer that people uses, which gives you the surface thickness or surface roughness. So it is an alternate, economical alternate to such type of system. Of course, if the movement of the bridges cannot be monitored physically, and if the movement is on a very small dimension, which of course over a period of time will going to get actuate, so it can also monitor that. And for biological monitoring, this is something which our lab are now working on to make some what are called as wearable photonics devices. So today we will not discuss about that, but in our lab we are trying to make a photonic based system which can monitor the different parameters of a human body. So this diagram just shows you that if you can use some bridge, you can place such type of sensor there, and then you can monitor if there is any movement within the bridge which is unwanted. So how does it work? So it works as follows. So it works as follows. So the point is, if you consider a SLED source. Now this SLED source is connected to, this is your sensing arm. You can see the sensing arm. So what does this sensing arm consist of? It consists of a fusion splice, single mode, and photonic crystal fiber. Now this is the D by lambda ratio which I was talking about. One can tailor this lambda, one can tailor this D, and can tailor the dispersion and therefore the property of the PCM. So if you have a SLED source which is connected to the source via circulators in such a way that one arm of the circulator is going to OSA and another arm is connected to the probe, and if you keep a highly polished reflecting surface very close, how close is very close? In the current system we have used 110 micron, very close to the sensing head, and now these highly polished reflecting surface can be controlled using some positioner, computer controlled positioner. Then what you will see is as follows. What you have plotted here is reflected power versus wavelength. Now without mirror, you see you have this dotted line. So remove the mirror. So you know that given length of the PCF will be there, core and cladding mode will get excited, it will interfere. Plus there will be some Fresnel reflection from the air and this tip of the fiber interface. Therefore you get some very nice interference pattern. But you see the peak of this, or the width or the period of this interference pattern is quite big. It's almost more than 20 nanometer. Now once we put these highly reflecting surface at the optimized position, at the optimized position, that means you'll not only have reflection from the tip, but there will be another reflection which is coming from the mirror. Now these two, the light being reflected from the tip of the interferometer and the light being reflected from the mirror, because the distance is very nearby, it tends to form interference within the interference, which is having a much lower period now. You can see that you get an interference within interference. Now, coming back to how far or how near we can close, please note that if you are very close, in our case it is less than 110 micron, then the period of one interference will going to overlap with the period of other. I mean the tip of one interference or the dip of another interference peak or dip will going to interfere with the other, and you will get some distorted interference like this. But if you are at a 110 micron and beyond, you get a very nice interference pattern. So what we have plotted here is wavelength of the dip. That means we have taken one of these. We have taken one of these dip, and then we have tried to monitor the distance. We have moved the distance, and we realized that in our case, that if you keep the reflecting surface at a distance of 110 micron, you are able to monitor the displacement much efficiently without disturbing the interference. Right? This is what it has been shown here, that D equal to 10. So 1 of the lambda. Now please note that the advantage of these type of system, unlike system like FBG and stuff, that you have a broad peak which is at your disposal. You choose any notch wavelength at whatever the source and detector available with you, and then you can integrate those things for your work. That means it gives you a lot of extra degree of freedom to work. So for example, in this particular case, we have chosen one of the peak, let's say which is at 1553, and then we have monitored that peak. Having said that, one can monitor any peak in this system. So you monitor D, when D is 110, your peak, here, and as you go on increasing, as you go on decreasing the value of D, one can see that there is a shift in the interference pattern. Now the point is how much is this shift in the interference pattern, and once we measure that, it turns out that for every nanometer shift in the reflecting surface, the interference pattern shift by 32 picometer. Now, with the current state of art or the system that are available, whether it is IMON or it is OSA, the resolution can go as low as 1 picometer. Therefore, measuring 32 picometer is much convenient. It's much convenient. And therefore, this type of system can be very useful if you want to have some precision alignment of position monitoring to a level almost of nanometer. Now, the same work has been further extended with mass cantilever system, as you can see here, mass cantilever system for the development of micro G accelerometer. Now, what I have shown here, it is the same setup till here, but now the whole system is in vertical mode. And then you have this gold coated mirror surface that has been created, and the external cavity has been shown, tip of this interferometer and this cavity. Now, the gold coated has been created on the mass to which you want to give the acceleration, which is connected to, which is connected to a system via cantilever. Now, all these need to be optimized. The length of the cantilever, the type of material that you have to use, and stuff, everything has been optimized. And this is what it looked like. The viewgram you can show, the device looked like something very similar to this. Now, the point is, when the measurement of accelerometer was carried out, we realized that it has a wavelength shift which is very significant in the direction of acceleration. Because acceleration, if acceleration is in, let's say, z direction, there is a good amount of chance that the system may measure the acceleration in x or in plane xz plane or xy plane or zy plane. But what we realized that for all other apart from z direction, that wavelength shift is insignificant or very, very close to zero. Unlike for all other case, the wavelength shift is very significant, going as high as, let's say, as high as 150 picometer. So what led to its patent is these advantages, that it can cater to micro G resolution. And the most important part of what I have mentioned earlier also, it has variable working range. When I say that it has variable working range, I basically mean that that you can tailor the device parameter. So how to tailor the device parameter? You can excite the mode very selectively, or not very selectively, I should say. You can excite the mode appropriately by choosing the way you create the collapse length, or by choosing the length of the PCL. And therefore, the range of working range can go from milli G to micro G depending upon your requirement. And all these systems are reconfigurable. That means you configure it as per the requirement. Apart from that, whatever the advantage any fiber-based system will have, it carries all those advantages. So this is what this work particular was for a DRDO. So where we have tried to develop this part. Now let me go to the next part of the talk, which is how to measure any strain using such type of interferometer. Now I have shown you in the very first figure where some of the structures that we have shown that we have developed. I think this is what we just showed you, that we have tried to trap air inside an photonic-crystal fiber. This is how we have trapped. So you considered a conventional fiber, you then, rather than a solid core photonic-crystal fiber, we considered a hollow core photonic-crystal fiber. And then we heat them at high temperature in order to heat them at high temperature in order to do a splicing. And then followed by that, you have to splice, and then again you have to do some sort of joining some single mode fiber. Now, if you can properly heat these area suitably, then you are going to trap these air holes which are part of the hollow core fiber. You can trap that to form a micro cavity or micro air cavity. We called it as a MAC, micro air cavity, and for which the length LA and LB can be tuned. We can control the length LA and LB. Now, why we are interested to control the length LA and LB? Please see in this diagram. So suppose if light is being reflected from front end of the cavity, micro MAC, which is I1, and it reflects from the second end of the cavity, which is I2, and these two interfere. So if you can tune this D, which will be basically is related to LA and LB, if you can tune this, then basically you change lambda, therefore you change the intensity. And if you want to monitor a strain, which is given by some lambda z by mu times epsilon z, which is the strain along the z direction, then the whole idea is you are able to correlate by tuning this D, you are able to correlate the strain. Now, this is the idea on which we worked, and you can see that we get a very nice interference pattern again over broad wavelength range. In the next slide, I will show you that you say that what are the parameter of major and minor axis you want is your requirement, depending upon what strain or some other parameter you want to monitor, and therefore we say it as a MAC on demand. Now, this is what is the MAC on demand. So we go from all the way from 10 micron to 14 micron, 60 micron to 105 micron, 30 micron. You see that all different diameter can be created. All different diameter can be created. So this is what we call as a MAC on demand. So one can create any number as per the choice. One can create any number as per the choice. So then we tried to had patent, and this is what it led to its patent, that we have found an easy method to create such type of air cavity for wide range of application and wide range of different parameters. These are easier process. Of course, there are other techniques that can be utilized, like focused ion beam that people have also used, but those are very costly techniques. So these are techniques which are economical, easier to develop. And these are some of the advantages you have. So what we did in our lab, then we tried to measure with the MAC, we tried to measure the sensing part, and as you can see that all the sensing and temperature and strain goes side by side. So typically if you consider any FBG based system, you will realize that it has a typical strain sensitivity of 1.1 picometer, unlike here what we have demonstrated, that this can be as high as twice as high as FBG based system, which are commercially available. So this is twice typically than FBG strain sensors. And you see here, it has a very low temperature dependence. Now this low temperature dependence is advantageous when you do the temperature measurement. We went further ahead to propose what is called as a dual MAC. That means we can make two cavity. Now you please note that here the dual MAC is something like you have first micro air cavity, then you have in between is a silica. So you have a silica cavity, and then you have a second micro air cavity. Now you can tune this. You can increase this size, you can reduce. So you can have, what we have shown here is all the different combinations. And then we have shown these are the samples which we have developed in our lab. And then we again try to measure the, this only shows you that which cavity is dominant. So if you take the fast Fourier transform of those spectra, you will realize that wherever the air cavity, in all the cases you see that the air cavity is dominant. But if you go for the sample 3 and sample 4, you see that hybrid cavities are also there, and therefore you can see a lot of these zigzag, which shows that apart from air cavity, you also have the cavity which are responsible are those small MAC that is there. So we went on to measure its strain value and also for different value with the strain and temperature. So as you can see that we have measured here with increase and decrease in strain. In this case, the value of strain is almost very close to 4.4. That means one can tailor the strain sensitivity, or one can tailor the strain performance by creating different structure within them. Such type of photonic crystal, using photonic crystal fiber, and then one can tailor not only the parameter of them as per the user's requirement. So here you can see that these are the numbers. It is almost like 4.1. Sensitivity is 4.1 wavelength shift versus strain what we have shown. And also for some of the cases, you can see that the temperature dependence is much smaller, because please note that these are shift in picometer, these are shift in nanometer. So it gives a very strong dependence on a strain, but very weaker dependence on temperature. Of course, this temperature dependence can be compensated using proper technique. So now this takes me to the another topic which I would like to discuss with you, and this is regarding gaseous detection. Now this is regarding gaseous detection. Now the point is when we talk about gaseous detection, the few things that come to our mind is all the different type of gases that are available in nature. And some are harmful, some are useful. But what I'm trying to give you the concept is how one can do gases detection or trace gas detection for any gases. So one has to be slightly, innovative in the approach, and you can do that. So in this particular diagram, what I am trying to show you is as follows. You see, these are low-cost devices. These are low-cost devices. You see, you have this special type of fiber, which is a solid core fiber. You can see here, and then these are the image that we have just shown you here. Now, if you have some sort of a chamber, gaseous chamber, inside which you lower your interferometer. Now, this interferometer is this fiber. Fusion is spliced with single mode fiber, which is going to form, thereby, fiber optic circulator, and you have LED and OSA as a system. Now, if you infiltrate this chamber with any VOC, this is volatile organic compounds. We know that there are a lot of volatile organic compounds that we come across in our day-to-day life. Most of us, whenever we enter some new car, you'll see that there's a typical smell that comes out from the leather. Those are basically VOCs. Or for that matter, even the nail polish that are utilized at home. You have a lot of VOCs there on. Also, even when we go to our washroom, you'll see that VOCs are present in different forms, whatever we use. So, therefore, it's monitoring or its detection because these are not very healthy. These are not very healthy. So if you infiltrate these VOCs through some, again, you need to have some syringe like that, which are computer controlled and stuff. If you inject them, then what happens? These VOCs molecules, they infiltrate the holes of this PCF. You see, it will get inside these air holes because the size of the air holes is of order of micron. These VOCs molecule are much smaller in size, so it get inside the air holes. Now, as it get inside the air holes, you will realize that now earlier it was air, now it is air which is coated with VOCs, or I said VOCs coated air, or air holes infiltrated VOCs. The effective index of that will be different, and therefore it will going to change the interference condition. It will going to change the condition for the fulfillment of maxima and minima in the interference, which can be correlated to the refractive index, what is there for a given VOC. So this is how it will going to work. So if you have different modes available which will going to interfere, so these interfering modes will have certain interference pattern. Now, with air holes as such, you get into one interference pattern. I have discussed earlier about this. Now you infiltrate with VOCs, you'll have an interference pattern which is shifted, and the shifting is interference pattern because around the air holes now you have VOCs, so the effective index changes around the cladding. Therefore, mode will travel at a different velocity again there. Now those can be correlated in such a way that you will able to monitor what type of VOCs are there. So this is what I have tried to show you here, that if you have isopropanol, for example, in air and an isopropanol, you get shift in the interference pattern. Now, if one monitor the shift versus time, you see that it gives you a very gradual shift. Whenever you inject something, it gives you some shift. After that, it remains constant over time. Again, you inject, it gives you shift. So this gets very periodical. It gets very periodically, it increases. And these are also, as soon as the VOCs dries up, it again comes down to its original position. So what is the response time of this sensor? If I have to tell that, how fast are these? So you see, this is the point at which VOCs was dispensed. So we are typically around, let's say, between 25 and 26 minutes. And during this time, 5 to 6 minutes, you will able to configure that whether the VOCs was present or not. In fact, you can start configuring, the response can be seen maybe within a minute. But then the total, this is a time, when the VOCs, you can think that this is a time when the VOCs have been sort of saturated and there is no further effect, and therefore the peak remains at that point. Now, such type of system can be very fast, and we have realized that these can go to sub-nanoliter concentration of VOCs can be detected using this system. So one can detect very low quantity of very low. I'm saying about less than 10 to the power minus 9 liter of VOCs can be detected using this. Okay, so this is what I have shown here, that for different VOCs we try to plot the shift versus number of VOC molecule, and as you can see that the detection limit is around 600 picoliter. This work has been highly cited at different places, including some of the Nature article, where they consider our work as a benchmark, where they say that these air holes can work as a micro chemical chamber or micro reactor sort of stuff, where all different chemical reactions can be done. So, and those numbers of what a small is typically hovering around these 600 picoliters. So, where these can be utilized, this can have applications in environmental monitoring, Excel grade analysis, or even the food that degrade over a period of time. It emits VOCs, can be utilized for food degradation analysis. Now, so in the last part of detection, what I have shown you is that we were infiltrating the holes of the PCF with VOC. That means these VOCs was entering into the hole. Now, you also have to, for the next measurement, you also have to remove those VOCs. Therefore, you have to heat it. Now, heating is again time consuming. Although I mentioned that the response time is fast, but then for the next measurement, when it will be ready, you have to heat the system. Now, we don't want that, because how many reading you will do every time you will heat, again you will make the probe has to be made ready. Then we come up with a new idea. Look, you don't have to infiltrate the holes. What you do, you fusion splice another SMF to create two of these collapse region. This is first collapse region, this is second collapse region. Now, rather than infiltrating the holes of the PCF with VOC, what you do, you put the VOC on the surface of the SCPCF only. Now you have the VOCs which is on the surface. Because I told you that the higher order modes are not confined. It goes away from the central core. And therefore these higher order modes will going to again change the interference pattern. You can see the shift in the interference pattern. And by that you will able to calculate what is the system or what is the index of VOCs or any other material. Please note that this particular area, what I am talking about, it has opened a new area of research. Thereby, this particular work has attracted more than 250 citations during this time, and still it is attracting, because this has just opened some new area of research in the research community across the globe. So now people have done a lot of the work on this, as you can see, some of you may have also seen that. Now, one just need to put around. You don't have to infiltrate like other. And this is what also we did. We did something, because till now, the questions that may come to you that, oh, you mentioned that, oh, it can detect a particular VOCs, but you never mentioned that can we precisely say that which VOCs was detected. And for that, you have to take help of material scientists, or you have to come up with a system where you have to come up with a system where you have to utilize some material, and this is exactly what we did. So we utilized this Pani and metal oxide nanocomposite, and then we coated those Pani and metal oxide nanocomposite around our interferometer, that is around the specialty's two-dimensional photometer crystal. Suitably we coated that. That's what you can think of. We suitably coated that around that with the also a lot of optimization and stuff it was done. These are some of the diagrams which shows that this is the length 140 micron. That means the collapse length in this case was 140 micron, optimized one. Now, so how does this work? I will going to discuss in the next slide. But you see, if you incident some light source, and if you plot, this is in transmission mode. Earlier we was discussing in reflection mode. This is in transmission mode. If you see, if you have some source which gives you transmission. So your typical transmission curve will be like this. Now, if you make an interferometer, you get interference pattern. This is what the interference pattern is. Interference pattern after coating with ammonia. After coating with pani and SNO2 nanocomposite. But if you expose this pani SNO2 nanocomposite to ammonia gas, you see the shift in interference pattern in real time. Why it happens, I will explain as we go to the next slide, but please see these numbers. These numbers are basically a state of art. Here, unlike the earlier case where we were talking about the response time typically hovering from few minutes, we are talking about the response time of second. That means now you can detect gases like, this is a concept for ammonia, of course it can be utilized for all other systems. The response time is second. Please see this limit of detection. We can go to femtomolar concentration, unlike earlier case where we have shown to nanomolar concentration. Since these are nanocomposites, you can reuse them. These results are highly reproducible. And of course, the application-wise, it's people can use it for environmental monitoring, especially for those trace gas detection. Let me explain you in slightly more detail how does the whole system works. You see, metal oxide this particular SNO2 can be assumed to be N-type semiconductor, and pani is P-type. Now, if you can imagine N-type, this N-type and P-type semiconductor will have certain depletion region. Now, pani is having some sort of a N+ atom which is centrally present there. Therefore, you also have some ammonium present in the system, NH4+. Now, if you have this depletion layer, as soon as it will going to come closer, that means you form the nanocomposite, you'll see that N+ atom due to presence of NH+4 will start moving. So you can see the movement of them. It's trying to go towards this side. Now, as it tries to go towards this side, it will going to squeeze the depletion region, and therefore the length of the depletion region, you can see that it is getting squeezed. So this rearrangement that is taking place is only when ammonia is coming into play. So as soon as you put the ammonia, it interacts with pani to form NH+ ion. Due to this, there is a rearrangement thereby leading to the reduce in depletion region, which basically increases the conductivity. Now, this increase in conductivity can be related to the change in the modal characteristics of higher order modes of the photonickel fiber, and as a result, you get a shift in the interference pattern. So this is the concept that we have proposed, and in general, this concept can be utilized for. Any gases that you want to measure, but only thing is you have to choose for the proper or suitable nanocomposite. Okay, so let me come to the last part of my talk. I hope I am fine with the timing and the stuff. Am I fine with the timing? How much time I have?
Sir, you have a lot of time left. You can
How
continue.
much? No, if you tell me accordingly, I can emphasize. So you please tell me about the amount of time I have left.
Sir, you have more than 40 minutes.
Session is scheduled to over at 1:30.
It's up to 1:45, sir.
1:45 now, but I was told to 1:15, right? No?
I think we can continue, sir, according to the information shared.
Okay, fine. Okay, fine. Okay, so the next part of the talk is, I will say that it is more interesting. When I say it is more interesting, because this is a work which we are in the whole process of on the verge of commercializing, and therefore possibly in near future we'll see that this is hitting the market. Okay, so this work has its own fate. It suffered the corona effect. So we were ready with everything in 2019, and then the company which was interested, international company which was interested to have this product, somehow withdrew, and now we are again afresh in contact with some of the companies for its commercialization. And also this project is funded by device development program of the DST for its Make in India program, development through Make in India program. So what is this? So what fluid flow measurement, when I say fluid, all of you know that fluid can be in form of solid, it can be liquid, or it can be gases, right? What we are talking about, the particular view graph, what you can show here, this is one of a instrument which is commercially utilized by different international companies. This one I am showing you from a particular international companies. So here you have the pipe which goes inside. Sorry, here you have the pipe which goes inside. Now you can see these two terminal and stuff. So our idea was, to develop where this gets basically attached to any pipe. If you have a gas pipe line, if you think of a gas pipeline, it will be cut from the between, and then you can just place these depending upon the diameter of the gas pipeline. So our system that we have developed can work for different diameter of the pipeline also. So let me tell you quickly that what is the principle on which we are proposing, or how we're going to measure the different fluid flow rate. So if we consider the principle of operation, I will go to the next slide. I will show you that if you have a number which is called as a Strohal number, which is defined by this F into D by V. F is a vortex setting frequency. So in our system, we basically measure the vortex setting frequency. D is the diameter, or whatever the cylinder you want to use, different diameter of the cylinder. And then V is the velocity. So basically, if we expect that for any fluid, one can define a Reynolds number. So if you plot Strohal number versus Reynolds number, it should be a straight line, almost constant. That means this is what any company working in the gas pipeline, which is almost very close to, if I remember the number, it is close to $8 billion or 26 billion. I think currently it is 8 by 2026. It's expected to be 26 billion. I have those slides also on some other PPT. It is expected to hit the market value for these all fluid flow monitoring, especially for oil, gas pipeline, nuclear power plant and stuff. It's almost close to 28 billion USD. Now, this is what the company looks for. They look for that for over a broad range of Reynolds number, your Strohal number should remain more or less constant. It is very challenging to keep them constant. I will discuss why it is challenging. So I will explain you. You just remember that you see that after a fluid hit a bluff body, I will explain what is bluff body. It is basically utilized to create the vortices, different vortices. So there are different type of flow meter that are available in the market. The one that we are talking about is a vortex flow meter, which basically creates these vortices as you have seen here. And that to create these vortices, you require some sort of a bluff body. What a bluff body? These are some metallic type of optimized structure which need to be kept in line with the flow so that you are able to create these vortices. These vortices thereby going to disturb the interferometer or going to interact with the interferometer, and it will going to give you certain frequency. You monitor that frequency, and then from there you measure the velocity. This is so again you see this is the probe that I have earlier talked about. Only thing is now we have metal casing. We have put everything inside a metal casing, and the choice of the metal and stuff is largely governed by the temperature at which you want to operate your system. So our claim or the work that we have done here, this vortex flow meter can work till 500 degrees centigrade, unlike the conventional flow meter that are available in the market, which are capacitive based. Basically the flow is measured in terms of capacitance. So those flow capacitive base can only measure flow till around 250 degrees centigrade. So we are offering a system which can go for a higher fluid temperature and also for a very low Reynolds number. This is the beauty of the system. I will show you as we go ahead with the slide. So once we have made our interferometer, it is cased inside some metal casing, which is decided by the temperature at which you want to operate. And then these are basically compacted. We compact this metal casing suitably with materials, so that whenever you have, because flow will come from this side. You see the flow will come from this side. So I will show you in the next slide. So flow come from this side. The momentum that is associated with the flow must be felt by this interferometer, and therefore compaction is required in this region. You have to make the region compact. So compaction is required in this region. So you can make the region compact. Suitably, one can do that. So whenever the flow comes, the flow basically hits this interferometer. Now, as it hits this interferometer, it changes the phase which are associated with a given mode in the presence of flow and in the absence of flow. Now, one monitored those phase, and then one can calculate the frequency from that. And after calculating the frequency, one can calculate the velocity. So this is I think again, how does your system look like in terms of when you have created this metallic casing, and you get some nice interference pattern, as you can see here. I mean, all these things, whatever I'm showing you, is after the casing. So metallic casing has other importance. It does not only saves your system from or provide more mechanical stability to your system, but at the same time, this metallic casing also allows you to get the system, your whole probe, contaminated. So why we have chosen this particular method for flow measurement when you have a cheap flow meter available or economical flow meter available in the market, which costs typically 30,000-40,000 rupees. Please note that our product is not aimed for to compete with this 30,000-40,000 flow meter based on differential flow measurement or capacitive based flow measurement or Doppler's based flow measurement. These are niche product which can be catered to the requirement to the flow rate what is not available in the market currently. In the market currently, there is no system available which can monitor the flow less than 50,000 Reynolds number. That means for a higher the Reynolds number, more is the velocity of the flow. So there is no flow meter available in the market which can give you a flow whose Reynolds number is less than 50,000. So therefore, we are looking for those markets where the Reynolds number, requirement of the Reynolds number is less than 50,000. Please note that. Having said that, I also mean that the system can also monitor, or it can also detect Reynolds fluid flow more than 50,000 Reynolds number. Our system can work till 5 lakh Reynolds number, starting from the one that we have tested in our lab, from 1,000 Reynolds number to 5 lakh. Please note that less than 1,000 Reynolds number is not the limitation of our system. It's the limitation of the detecting unit that we have currently available. But in principle, it can go to even less than 1,000 hertz or 1,000 Reynolds number. Okay, so this is the USP which led to its patent, that these are highly sensitive even at low flow rate. How low we are talking about? We are talking about Reynolds number in the range of 1,000, 2,000. These are online retract. Suppose your pipeline or gas line is open, and it's fully operational, and you have some problem with your flow meter. You don't have to shut down the plant like what people are doing currently. These can be retraced. You just have to remove the probe, and then you have, while the flow is being moved, I will show you that you just have to drill. You just have to drill a small probe. You just have to drill a small inlet in your gas pipeline, whose size can go from around 1 millimeter to 2 millimeter, between 1 millimeter and 2 millimeter. You just have to make that drill inside the pipe, and then you can put the probe there. So these can be online retractable sensor design. That means you can online, while the system is on, still you can monitor. As I mentioned to you that these are reliable under high temperature applications. If the fluid temperature is high, still it will work. Needless to say, these are based on silica. Therefore, these are immune to electromagnetic waves. Please note that whenever you have used these electronic sensors, which are capacitive based, it is not very conducive. It is not very conducive to use such type of systems where you use oil and gases. Many of them are quite conducting. So that is not well appreciated at the time. Of course, people does take proper precaution for that, but when we talk about one-to-one advantage and disadvantage, these are immune to electromagnetic waves and radiations. The system that we have developed are really small. I don't think I have put the design of that or photographs of the system here, but these are very small. So you can think it can go inside. It can go inside. The whole probe can go inside a floppy disk. We used to have. Now we have a CD box, a small one CD where you can keep one CD. The whole system can go inside that CD. When I say the whole system, I only mean the probe, not the detection unit, whole detection unit. These have very high resolution. You will see that, and it has low cross-axis sensitivity. So we don't have any cross-axis sensitivity, and it can be utilized. This is what we have further. I'm not presenting there. We have further extended our work where we have tried to monitor the flow at different locations. Let's say, assume that at different locations you have different type of fluid that are moving. So can one integrate and determine the different fluid at different locations? So we can also predict now with using machine learning technique. We can also predict that which particular flow meter is operating at which particular flow by looking at the data. So that is the strength of the work that is going on. So this is how the casing or development process start. With that, you have this. You can think of this as some sort of a piece of photonic crystal fiber. Then you have this single mode fiber. You put them together. Then you form collapsing of SMF and PCF. You get some kind of this structure, and then you put it inside metal casing. This is the testing bed what we have available here in our lab. So this testing bed, as you can see that you can read here from here that one is your flow control valve, because this is the electromagnetic flow meter. At 2, you can see that this is what I was talking about. This cost around 30,000-40,000 rupees. So for calibration of our probe, we have utilized this electromagnetic flow meter. Now you see, this is the probe I am talking about. This is our whole probe. So it's just going inside the pipe, right? And then this probe is coming. This probe, you can monitor it on PC. You can monitor it on laptop. In our lab, we have monitored the whole system on our laptop. And then you see that this is the IMON that we have used. It's some sort of a detection unit. You can see that. And then the whole system, this is the pump. Fluid is being pumped through this pipe. And then whole process, it's come from here, it goes from here, you monitor the flow, and then it comes back again back to the system. So this is where the test bed where we have. This is the test bed where we have, utilized our system. Now you see, the one that we have used for commercialization gives you such type of waveform. So now this is in our control because I have mentioned earlier also that these systems being reconfigurable, you can, in our lab, we can make any number of these. We can increase, decrease this width. Therefore, what I'm trying to tell you is that in the lab, depending upon what user want, we can play with this, how we can get them. So, but the one that I have shown you is the one that has been patented and also the one that has been in the process of being commercialized. So these are the waveform, what it look like. And then you see this is what I have shown you is some real picture of the measurement. So these are the numbers what I am talking about, 0.32 meter cube per hour. So you see, this is the frequency which it picks. So you see that these are noisy. Please note that there is no signal processing that has been applied now. We have also realized that without signal processing, the SNR, signal to noise ratio of our device, is better than what is commercially available for low, not for low Reynolds number, what is commercially available for high Reynolds number. So you can see that this is the frequency which we are talking about, and this corresponds to around 0.32 meter cube per hour. So the beauty of the whole system is that it can detect, if you calculate the Reynolds number, it will turn out to be something very close to around 4,000, that what I have shown here. This will be close to 3,500, 600, I think. It will be close to that Reynolds number. So this is what, one of the results that I have shown you here, just to tell you that this is the real time data picture what you get. Okay, now what we have further went ahead is not only with, in flow in one direction, but we can also monitor flow in either direction. That means our system can say, without really, looking, that which side flow is coming from. So if it is from the forward direction and if it is from the reverse direction. As I was mentioning to you earlier about the bluff body, so it is some sort of a metallic design. This is the trapezoidal bluff body that has been utilized, and that are basically utilized for conventional flow meter. And this is a special type of, you can see that this is in between. It is a cylindrical structure. In the center you have cylindrical structure. So this is a bluff body. This is a bluff body which allows you to monitor the flow both in the forward direction and reverse direction. So as I've mentioned earlier, as the flow propagates, it basically creates these vortices, and your interferometer start to respond to different frequencies, and you monitor those frequencies and determine the flow. So I will like to conclude my work here, that what are the different advantages and disadvantages of our work. I mean, I have been trying to be quite crisp with the, I have been trying to just be crisp with, especially with the flow meter, keeping in mind the time which was in my mind, that I have to wind up at 1:15 around. So keeping that in mind, I have tried to not give you the further more details about that. So the point is here, what are the different impact of this research? So what are some of the sensor technology that we have developed, keeping in mind that the future smart cities are in future smart cities is in process. So these can be utilized for real-time monitoring of a structural health monitoring, water level monitoring, and environmental conditioning monitoring. With respect to accelerometer that I have discussed, it can be utilized for micro-G accelerometer with micro-G resolution for defense and aviation sector. With respect to the nano displacement center, one can monitor the precision alignment and position monitoring for space applications. Fluid flow is something which is coming quite nicely, and I see that this has a lot of potential in the near future. Further, we have extended this work of fluid flow. Now we have come up with another system where we can condition the signal inside the pipe from outside. That means if the signal is being attenuated inside the pipe due to some reason, or let's say with flow something came all of a sudden, and then your signal get decreased automatically, then from outside we can control that signal by suitably operating at particular suitably operating at particular frequency. So that for no time, I mean throughout the measurement, your flow can be monitored precisely. Even if the signal to noise ratio decreases, we can still enhance the signal to noise ratio. And this we have tested. For low Reynolds number starting from 1,000 to as high as around 50,000. So the current system that we have developed, it can not only attenuate the signal, inside the pipe. So, but we are not doing anything with the probe inside the pipe. We have a control probe which is outside. So it can attenuate the signal, not only attenuate the signal inside the pipe, it can also amplify the signal. It can also filter the unwanted noise in the signal from outside. So we can control the probe from outside. So that we have again, the patent filing is in process for that. So there are quite a bit of other things that is being done in the lab, which I have not tried to cover here, but these are some of the things which I thought that will cater to wide audience, ranging from different departments, starting from mechanical, electrical, applied physics at large. So we do believe that some of these things will be in the land very soon. Some of them have been already tested at different places, but towards the commercialization, we are working on that. So needless to mention that this slide is the most important of all, because I considered IIT Bhubaneswar gave me the platform to work, but this platform would not have been utilized or not have been beneficial without my students. So I am really thankful to all my students, who have worked day and night, and still I'm sure that they are working in the lab, and therefore while I'm presenting with you. So Dr. Pradeep Maharana, he was my first PhD student. He is in job currently here. Then Dr. Jitendra Narayan Das, he is my second PhD student. He is doing his postdoc from City University, Hong Kong. Dr. Anand Mohan Srivastava, he is doing postdoc at Israel. Dr. Gaurav Sharma, he is working as a faculty in one of the colleges in Uttar Pradesh. Sumit Das is working as a faculty currently at Kitch University here. Chiman Naik is doing postdoc. And these are some of my students. These are some of my students who are still working with me. I must thank all my collaborators for his collaboration as and when required, and SCRB Star Fellowship by the Government of India, which have been recently given. And needless to mention that as an experimentalist, without the support from these people in terms of the different funding that I have been getting quite regularly, these work would not have been possible. So I must acknowledge DST, DRDO, DBT, and HRDs for all the funding support. And thank you very much. Lastly, for your kind attention, I will be happy to take any questions.
Thank you, Dr. Rajan sir. And really, you have shown us the theory from very basic to the device one, and it is really very nice for us to have an experience of how the photonic devices are working and how the applications have been developed in the labs. So I welcome all the questions, if any. Please ask the questions if anyone have.
Can I stop sharing, or do I need to?
Yeah, please. I think you may stop.
Okay, I would love to take the questions if there is any from the audience. Or so, maybe I may be, hanging them from there. I'm between their lunch. So possibly some of them may be in a hurry, but I think Ankit Singh has asked something. Is ammonia dependent upon material? Yes. Yes, Ankit. So Ankit, is ammonia detection dependent upon material properties? Yes. Or the structural property. It is the material and therefore the structure. It's not precisely on the structure properties. If you see the Pani SNO2 nanocomposite, then it tend to form certain. I have not shown you there, but when we did the FAPCM and PM result, we realized that these the structures allows you to ammonia to get entrapped inside some of the micro and nano holes which are formed all around the nanocomposite. So as it forms all around the nanocomposites, these ammonia gas get inside and then it interact with these SNO2 Pani nanocomposite to form what is called as NH+4 ion, thereby modifying the modal effective index around the probe, which leads to the shift in the interference pattern. So yeah, it's material dependent and therefore structural dependent.
Yeah. Any other question? So if not, if anyone have any question, even later on, you may write to us and we will communicate with Dr. Rajan sir. And let's thank again Dr. Rajan sir. And when he was mentioning about his collaborative group, he was mentioning about his first student. So we understand that the first student always had a lot of experiences in the lab. So really very nice one, sir. And thank you. Thanks a lot for giving us time. And,
thank you. My pleasure.
And for a really very nice talk.
Thank you. Thanks a lot. Thank you. Please feel free to write in case there is any problem with anyone. Please feel free to write. I will get back to you.
Okay, thank you, sir.
Thank you, Akhilesh sir. Thanks a lot for this opportunity.
Thank you, sir.
See you. Thank you. Thank you.